Hi, it's Terry Dennery of the MathWorks. In this video, we're going to talk about some MathWorks partners. Let me bring this up. Okay, um, I call it MathWorks Mechanical Partners. And so in the two previous videos, we saw featured the tool SimWise 4D, which I believe is a great way to build your mechanical models. And it's got a great capability to deliver mechanical models to Simulink in a form that is incredibly useful for me. Okay, that's the two previous videos. So there's an additional tool, and probably the next video I'm going to create is going to be called something like Fast Mechanics, or Fast Mechanics is great. Okay, and so that's going to bring in this tool called MotionGenesis Kane. And so this is a tool that was developed by one of my really good buddies, a guy named Paul Mitige, who teaches mechanical dynamics at Stanford University. Right now, the word or the name Kane is put into this too because Paul was one of Kane's students, graduate students. He did his PhD with Kane, and when he was working with Kane, they collaborated to create a symbolic tool that takes Kane's method for expressing mechanical dynamics equations um, and delivers it through a symbolic tool. So you get code that's like super fast for mechanics. That's the basic idea. And Kane's method is pretty famous, and certainly he had a tremendous impact on how mechanical simulations take place because he really focused very effectively on the numerics of mechanics. So hopefully that's a good introduction, and certainly he was super valuable. Okay, so anyways, let's kind of go back to where we finished the last video. And we finished right here, right? We had our mechanical assembly, right? Now there's a little piece that I didn't get into there, but I think I now kind of have the ability to explain why this needs to be done. And that tools like MotionGenesis are very precise on mechanics. And what the way I want to kind of maybe point this out is take this revolute joint. I'm going to split it. All right. Okay, and so what I think is kind of interesting about this is if you look at this from the top view, all right, and what clearly takes place, this is true whether that's split or not, but that this assembly is designed to kind of move in that single plane, right? Now, why is that important? Well, it means that the model as built is over constrained, all right, and it might seem like a very subtle point, and certainly tools like SimScape Multibody and SimWise, pretty much most of the tools that do this, can kind of live with that over constraint. But precise tools like MotionGenesis that really are looking to optimize everything, um, it's a good idea to do what I'm about to do. Okay, and so we're going to focus on this guy right here, right? And again, I think I'll look at it in wireframe. We see hopefully that cylinder. I'm going to double click on that joint, and we'll see that we can very easily change its, I'll call it constraint. And right now it's kind of constrained, so no rotations about X and Y, but a rotation around Z, and no sliding, meaning that the origin of the two frames that make up that joint are constrained to stay together. Okay, and so what I'm going to say is, well, because of the connection with the other links, that the constraints on X, Y are already happening, and that we can do this and it's still going to work. And I'll prove it. I hit run, it still moves just fine and no error statements. The other thing that's available actually is for Z to be able to translate. But again, because of the additional constraints, that's going to happen anyways, right? And so this is essentially reducing kind of the number of constraints on the system to really match the true degrees of freedom of the overall system. And for the most part, a four-bar linkage is a degree of freedom system, degree of freedom of one, meaning that there are two states, position and then the positional velocity. And that's why as we solve dynamics, we initialize both position and positional velocity. So hopefully that wasn't too technical, but I think it was important to kind of get us there, right? And so now what I want to do is I want to save this in that form, and let's go ahead and bring it in. And so I'll get back to MATLAB, get on apps, and go to get geometry, and again it will import the active document of Simulink. I'm sorry, of SimWise, which is one, of course, we're just looking at, right? And so we went through this, I guess, like 2 videos ago, and it's going to generate a Simulink model, which just showed up. Fortunately, you don't really get the drama of seeing all this stuff added into it. There's going to add a little bit more, but as it's essentially loading up the Simulink model with all the blocks that represent that mechanism and putting all the appropriate parameterization, we'll see all that stuff kind of come in. So we really just had this before it just created all this for us. And there we are. It's kind of funny how there's a little bit of delay before I can hit that run button. But I guess that'll give me a little bit of time to talk about, again, I think I've talked about this before, the data that's being filled into our workspace. Anyways, so let's go ahead and hit run. Okay, and we have a nice confirmation that it put together properly. There you go. All right. So anyways, what I want to get at now is kind of the nature of the partnership as it exists with MotionGenesis right now. We'll kind of see that what we did with SimWise was we created an input deck. That's what these are, right? And so this one called Terry Forbar, the FD, right? And you'll see it was just created. I'm doing this video on August 13, 2021. And so it time dates it for us. But essentially that get geometry wrote this file for us too. And this is the input deck for MotionGenesis. So I think I'll go to this line right here. So I'm going to just copy all this. All right, and certainly you could just input it directly into MotionGenesis, but I kind of like, watching what takes place here. And so I'll just kind of paste it in, right? And so MotionGenesis is a symbolic manipulator, and it's operating on all those lines of code in the input deck that essentially describe this mechanism. And it's very similar to SimScape multibodies, based on bodies, joints, and coordinate frames. Bodies have mass, inertia, so forth, and all that same sort of thing. What I think is really cool, this last command that we're about to run, essentially, what's the right word? Well, whatever. It's running the command ODE, which is going to generate the equations of motion, and it's going to write them in a .m file. Now, if I made that .c, it would write it to a .c file. So most symbolic tools, and certainly MotionGenesis, in a way, their main function is that they're great at generating really good code. At least the really good tools do. And so before I let that last command run, I am going to bring your attention to the name mgterry4bar.m, show that it doesn't exist in this directory right now, but when I hit enter, I think we'll see that it is created, which it is. All right, now we'll open that up. And this is what was just created for us by MotionGenesis, right? And again, it's absolutely a pretty efficient expression of the dynamics, and we'll see some things that might look familiar, but essentially second order derivatives are being calculated and all that kind of stuff. I'm going to just hit run for right now, right? And so we'll see within MATLAB, and I might want to fix some of these things with regard to the warning messages, but excuse me for that right now. And what we get to is that it just calculated that mechanism for us, and it gave me an easy way to plot it. All right, and so let's just evaluate that expression. And there's our calculation, right? Now, we're going to do a lot more with it than just this, but it's very exciting to see that code has been created, pretty compact code, and that there's a means to bring into Simulink to really support what we're doing with this project. So, thank you.